Representing knowledge is a very wide and amorphous topic in artificial intelligence, and also a vital one. Intelligence without some sort of knowledge is virtually impossible, and if you look sideways at just about any AI application and squint, you can see some sort of knowledge representation. After all, a chess-playing program knows the rules of chess. It doesn't know what chess is as such, or that winning at it is considered better than losing, but it has a representation of the rules of chess built into it. Knowledge representation goes hand in hand with automatic reasoning, which involves using the knowledge base, the set of facts, entities and relationships between them that the program knows, to deduce new conclusions that inevitably follow from it. One implication of this is that, for any given knowledge base, artificial intelligence is only useful if that knowledge base is incomplete. After all, every single fact and conclusion was stored in the knowledge base, then what use would AI be? Instead of having to derive the conclusions, the computer would simply look the appropriate entry up and report it, like some sort of complicated database. The size of a complete knowledge base would also quickly become unmanageable as the number of entities and relationships in the knowledge base was increased to a useful number. For example, consider a knowledge base that is a family tree. We store the basic relationships between the 8 people in the form of 7 facts. These describe the knowledge perfectly. If the diagram at the top of the screen were missing, you could reconstruct it from that information. If you wanted to answer the question, who are Sarah's grandchildren, it would require reasoning and a knowledge of what is meant by the term grandchild, not mentioned in any of those 7 facts, but it could be done. Alternatively, a complete knowledge base would look like that, or rather it would start off with that. I have listed the relationship of Brian to every other person, and of Sarah to every other person. Now the answer to the question, who are Sarah's grandchildren, can be found by reading off the appropriate lines. No AI necessary. This knowledge base contains an answer to every question you could ask about this family tree, but comprises hundreds of statements like the ones above. Knowledge representation and automatic reasoning are such broad topics that they form the major part of fields such as expert systems and production systems. I will be producing videos on both of these in time, so I'll say no more about them here, other than when I do, I'll be rehashing a lot of what you learn here. They are also the basis of areas such as microworlds and frames. Again, more on those in future videos. Indeed, so broad are knowledge representation and automatic reasoning that I have to chop it down to the most general of overviews. If I miss some aspect of it that you cherish, and I probably will, then please do leave a vitriolic comment below, and I will try to produce a video that remedies the omission. The automated reasoning part is achieved by applying logic, such as first-order logic and forward and backward chaining, to the individual relationships between the entities in the knowledge base. The conclusions drawn at each step are simple, but when strung together they enable connections between objects in the knowledge base which can be quite distant, in much the same way that a journey of many miles can be made up of simple short steps. I'll be explaining first-order logic in detail at a later date, but there's more about chaining later on in this video. The main area of knowledge representation that I'll be explaining here is semantic nets, as they represent knowledge in its most general form, not tied to any particular application. This is a semantic net. It takes the form of a directed graph, a series of nodes representing objects or concepts, joined by arrows representing the relationships between them. Arrows are used rather than simple lines to indicate which way round the relationships are, which is why we use the term directed graph, rather than an undirected one. The directed nature of the graph is what informs anyone seeing it that sparrows eat worms, not the other way round. There are 4 types of relationships here: is-a, eats, and can, together with its opposite, can't. Some of these relationships are transitive. This means that they can be extended from one object to another along the arrows. For example, the is-a relationship, or is an example of relationship if you like. The semantic net tells us that a mouse is a mammal, and that a mammal is an animal. We can conclude from this that mice are mammals, because is-a is a transitive relationship. Through similar logic, we can conclude that Henry is an animal as well, because we can trace arrows marked is-a all the way from Henry to animal. One other property of the is-a relationship is that it allows objects to inherit the qualities of all entities of which they are examples. If we ask the question, is Mickey warm-blooded, then we would find the entity, the node on the graph that represents Mickey. There is no relationship directly from Mickey to warm-blooded, but that doesn't matter, because if Mickey is an example of some other node which does have a link to warm-blooded, then we can answer yes to the question. Fortunately, there is a relationship from Mickey to another node in the graph, namely mouse. There is no direct link from mouse to warm-blooded, so we repeat the process and hunt around for another relationship from mouse. We find one that takes us to mammal, and this time there is a direct link to warm-blooded. Mammals are warm-blooded, mice are mammals, so mice are warm-blooded. Mickey is a mouse, so Mickey is warm-blooded. Please note that if we had not eventually arrived at a node with a connection to warm-blooded, the correct answer to the question, is Mickey warm-blooded, wouldn't be no. It would be, I don't know, or not as far as I know. Just because we couldn't track a path from Mickey to warm-blooded doesn't mean that he isn't. It might just be that particular information hasn't been added to the knowledge base. Similarly, if we are asked, can Tom fly? The correct answer is, I don't know. Birds generally can fly. In fact, if you ask people what sort of things they associate with birds, they will generally include flight as one of them. That's why it is perfectly reasonable to put in a can relationship between nodes bird and fly. However, ostriches are one of the relatively few species of birds that are flightless, so the correct answer to the question, can Gertrude fly, should be no. We shall therefore add in a relationship specifically between ostrich and fly, specifying that no, ostriches can't fly. With this exception in place, we can go ahead and ask, can Gertrude fly? We find that there is no direct link between Gertrude and fly, but that Gertrude is an example of an ostrich. OK then, try ostrich. We find that there is a direct link from ostrich to fly, telling us that, in fact, ostriches can't fly, and therefore Gertrude can't either. It's true that ostriches are examples of birds, and if we had gone one step further, we would have found that birds can fly, but we stopped as soon as we found an answer to the question. This conclusion, of course, does rely on the system realizing that can't is the opposite of can. A great deal of human knowledge cannot be fitted so neatly into such a simple diagram, of course. What happens if we wanted to add the concept of pet to that diagram? You could set up relationships from cat and mouse to pet, obviously, and from other animals that we'd added, such as dog or horse. But that would imply that all cats and mice are pets. Many of them aren't. Indeed, the vast majority of mice are wild and are considered vermin. You could always set up a relationship that specifies is often or is usually to indicate that cats are usually pets or that mice are often pets. However, how will we then stop the AI from concluding that Mickey was often a pet or that Tom was usually a pet? No, this sort of nuance can only be accommodated by adding further categories such as pet mouse or domestic cat. To capture all the subtlety of a real-world system, the knowledge base has to become many times more complicated. What we have been doing in tracing from specific animals such as Mickey and Gertrude in towards the general all-encompassing node of animal itself is an example of forward chaining. We start with a particular node in the graph and aim for a goal, which is the answer to a question we're trying to get. The reason it's called forward chaining is because we're following the direction of the arrows. Here's another example of forward chaining, this time using the sort of rules that we might find in an expert system. If A flies and A is a mammal, then A is a bat. If A lives in the ocean and A is a mammal, then A is a cetacean, that is a whale, a dolphin or a porpoise. If A is a bat, then A is nocturnal. If A is a cetacean, then A is intelligent. I am reading an encyclopedia entry about a mammal that lives in the ocean. Is the animal intelligent? Well, yeah. Just by looking at the screen, you can see that I must be reading about a cetacean. But how would you conclude that using forward chaining? Well, we know that the animal is a mammal and lives in the ocean. This matches the if part of the second rule, so we can logically conclude that the entry is about a cetacean. This then matches the if part of the last rule. Since the text is about a cetacean, it must be about an intelligent animal. The goal is reached. Now I read another entry in the same encyclopedia about a mammal that flies. Am I reading about another intelligent animal? This time the known facts match the if part of the first rule, so that we can conclude that I am reading about a bat. However, there is no rule that tells us whether bats are intelligent. I am definitely reading about a nocturnal animal, but we don't know whether it is intelligent or not. We have no reason to conclude that bats are stupid, of course. For all we know, there might be a species of hyper-intelligent bats out there, but that information is simply not included in the knowledge base. The flip side of forward chaining is, of course, backward chaining. Going back to the first encyclopedia entry about the ocean-going mammal, we answered the question, is the animal intelligent, by starting at the goal and working backwards. Is the animal intelligent? Okay, what do we know about animals that are intelligent? Well, the knowledge base tells us that cetaceans are intelligent. So the next step will be to work out if I were reading about a cetacean. This is a new goal, a sub-goal of the problem lying somewhere between the final goal of determining intelligence and the raw facts in the encyclopedia on the desk in front of me. Of course, there might be other rules that tell us that chimps are intelligent, and so are parrots. So in practice, we would be faced not with one sub-goal, but with several. If any one of them is satisfied, then we would have enough information to reach the final goal. Let's just stick with cetaceans, though. Right, how do we determine if the animal is a cetacean? There is one rule that lets us do that. As long as the animal lives in the ocean and is a mammal, then it's a cetacean. Both of the facts that we know fit this rule, so yes, the animal is indeed a cetacean. This fulfills the sub-goal, meaning that we can now answer the main question. Backward chaining is a rather roundabout method in this case, and that is because we start with the raw facts and try to work towards answering the question. Forward chaining is therefore the natural approach. Had we just started with the question, am I reading about an intelligent animal, and nothing else, then backward chaining would have been made more sense, and we would gather data as we went along. Going back to that original semantic net, backward chaining would be used to answer the question, which animals eat worms? We would start with a node for animal and work backwards until we reached every node joined to worms by a relationship for eats. So there you are. A quick skip and dance through the complex field of knowledge representation and automatic logic, showing how facts and statements about the world can be stored explicitly. Since the subject is so universal in AI, I will almost certainly return to some aspect of knowledge representation in a future video. In the fairly near future, for instance, I will be showing you how such a knowledge base can be hooked up to the version of ELIZA that I showed you last week, to make our conversations with the computer a little more intelligent. That's the end of the video. As usual, please do subscribe to the channel and click on the small bell icon if you want to receive news of my weekly videos, particularly if you want to implement the ideas that I describe in the form of JavaScript programs. Also, don't forget to click the like icon, or indeed the dislike icon, in which case you might like to leave a comment below explaining exactly where you think I went wrong. Thanks.